Welcome to BKW Physics. I'm Mr. McConley, and today we're going to expand our talk about waves to include the electromagnetic spectrum. Because we've been focusing, we did transverse longitudinal, we've been focusing a lot on sound. Now wrapping up, or moving away from sound, we're going to focus on the electromagnetic spectrum, which is made up of electricity and magnetism acting together to produce an electromagnetic wave. We'll get to the chart in a second. First thing you need to know is that all the things on this chart, which if you can't read them on the video, this is a direct picture from your reference table, your physics reference table. So you got gamma rays, X-rays, ultraviolet, infrared, microwaves, TV and FM radio, radio waves in general, AM and then long-range radio. And then stuff in between ultraviolet and infrared is a narrow slit called visible light. So people in the classroom, you don't have to copy that part down because it's all in your reference table. If you want to open your reference table so you can kind of refer, that'd be fine. Main point. Everything on this chart travels at the same speed. Just like all the sound waves traveled at 331 meters per second, everything on this chart travels at a speed, and that speed is 3e8. 3e8 meters per second. Very fast speed. To give you an idea how fast, this means that the light can travel around the globe 7.5 times in 1 second. So, one Mississippi, light can go around the Earth 7.5 times. That's almost, it's unfathomable how fast that is. It's just ridiculous. That being said, I want you to kind of frame your mind for a second and think about, I think people have told you that it takes like 8 minutes for light to get from the sun to the Earth. So if it's traveling the distance, you kind of can think about how big the distance around the Earth is, and in 1 second it goes around 7.5 times, but it takes 8 minutes to get from the sun to the Earth. Think how far away the sun is. Just ponder that thought for a minute. Okay? It's a long way away, in summary. So the C is specifically used when you're talking about light. Okay? So when you're talking about the speed of any of these, a lot of times people will just use the letter V. Speed is, velocity is 3e8. But when you start talking specifically about light itself, they use the C, because C is celeritis, and it's a constant, when light is traveling in a vacuum. So, we know that light will slow down when it goes into glass. We talked about that before. Light will slow down when it goes into water. Light will slow down even in air a little bit, okay, because air has a few things that will slow it down. But if you're in the vacuum of space in between the sun and the Earth, it's going to travel full speed ahead at 3e8. Alright, let's study this, or let's look at this chart for just a minute here, make it a little bit clearer. The way you read this chart confuses some students, because if you look at the top here, that says wavelength, lambda, wavelength. And if you look at the numbers 10 to the negative 13, 10 to the negative 7, 10 to the 1, 10 to the 4. So what can you say about the numbers as you go this way? As you go to the right, the numbers get bigger. That makes perfect sense to most people. And when you think of gamma rays, you're thinking of scary stuff that happens with maybe like a nuclear bomb or something like that. You know, most people know that gamma rays are not healthy for you, and it's mostly because they have a very short wavelength, and they seem to get right in your body and do damage to your cells. Okay, you go this way, this stuff gets safer and safer. Most people are not scared of standing in front of a TV or a radio or anything over here. It's not scary stuff. But it kind of does beg the question, or reinforces the idea that, you know, we talk about how you're not really supposed to tan yourself all the time or stand out in the sun constantly without any sunscreen on. And if you look at this chart, it might sort of make sense to you, because if this stuff is the long wavelength, seemingly safe, where is the stuff that hits you from the sun? kind of in this, obviously you got the visible light right in the middle, but you're also getting some infrared and you're getting some ultraviolet, neither of which is all the way to the right. And in fact, ultraviolet overlaps with X-rays. And pretty much if I told you guys I was going to X-ray you every day, you would get a little scared and you'd probably like, I'll ask my parents first. So, you're thinking like that's not that safe, but yet that's what the sun is. The sun is giving you waves at that frequency. Hence the reason it damages skin eventually. And when you get a suntan, what's it doing to you really? It's just because of the wavelength that's kind of burning the top layers of the skin, and that's the suntan. Now, if you look at the bottom part here, this is where people get a little mixed up in their mind, because that says 10 to the 21, 10 to the 14, 10 to the 5. So what's happening with the numbers here? Actually, if you're talking about getting bigger, the frequency is getting bigger going this way. So the wavelength is getting bigger going this way, the frequency is getting bigger going this way, which should kind of make sense, because if you remember, V equals F lambda. If this number is always the same, and it's 3E8, then as this one gets big, that one's got to get small. They work in opposition to each other. Okay? I think the other thing that confuses people is a lot of you memorized when you were kids a little saying to remember the colors. Roy G. Biv. Like it's a name. Well, some of you did, some of you didn't. Red, orange, yellow, green, blue, violet. But most of the time when people showed it to you, it was the other way around. Okay? So this is Roy G. Biv if you read backwards all the time. Okay? So violet being the highest frequency, but yet the shortest wavelength. Okay? Red being the lowest frequency, yet the longest wavelength. So that's kind of the way the chart works. And I guess what it does is it begs the question here, if light can travel around the globe 7.5 times per second, then how did we ever figure out the speed of light? It seems like impossible that anyone could have figured that out, because that's such a high number. So let me tell you a little story about that. So the early Greeks even thought about this, and they tried to make some measurements, and they were totally unsuccessful. They couldn't figure out the speed of light at all. Galileo was a smart guy, and he figured out a lot about gravity. He tried dropping things and timing them, but of course his time devices were totally inadequate for speeds the size of the speed of light. He had almost no success. Ole Romer was the first guy, and I'll just write it down if you're interested. You don't really need to know Ole Romer, except that he was the first guy that came close. What he noticed is he was watching one of Jupiter's moons, Io, and he watched the moon, and then he noticed that when Io was moving away from him, as opposed to towards him, because Io was going around, that he kept coming up with a different time. The times didn't match for the coming towards as versus going away. And he's like, I know that's not true, so what's going on here? And what he figured out is that, because since it's moving away, there's kind of like this lag in time, and he started doing some calculations, and he noticed it was actually 16 minutes difference for the orbit as determined by which way Io was moving. And he came up with this rough estimate of how fast he thought light must be traveling. It wasn't that far off, though, which is interesting. But the guy that gets the real credit is Albert Michelson. Albert Michelson is the guy you got to know. Albert Michelson was an American physicist. He lived from 1852 to 1931. And here's what he did. He had an octagon that was on a pivot point that was able to spin. And on this spinning octagon, he had one side that actually had a mirror on it. Okay? So I'll just put a little blue there to indicate the mirror. And then he had a light bulb, probably a pretty strong light bulb. And this light bulb obviously is giving off light, but when this mirror was right here, the light would hit the mirror, and because of the angle of incidence equal the angle of reflection, that's what we just studied with reflection a little while ago, the light would bounce off and head this way. That makes sense so far? When the mirror's not there, the light doesn't bounce off. Okay? Then it goes all the way down here, and it hits a curved mirror, which bounces it this way. It hits another curved mirror, bounces it back. Basically what he's doing is he's just trying to get the light to move over a little bit. And then the light comes all the way back this way. Now, if this mirror has moved, so now the mirror is here, let's say, what will happen? Well, if the mirror is there when the light gets back, it'll bounce off, and then here's Mr. Michelson standing down here. Oh, I can see light. It must be timed right. If he doesn't see anything, he can adjust the speed and make it go faster or slower until he gets it timed perfectly so it's going down and back, bouncing up. So all he does is, since he knows the RPMs here, revolutions per minute, he can figure out, divided by 8, and he can figure out how much of a turn he's talking about. Then he needs a distance, and he can just measure the distance. He can do velocity as distance divided by time, and he can very accurately get the speed of light. He did. He ended up getting that the speed of light is 299,792,458 meters per second, which we round to 3e8 meters per second. He got a very exacting number. One more thing before we wrap this up. How far do you think this distance was from the mirror thingy to the other mirrors? A good distance. In fact, 35 kilometers.
Oh, very distance.
Very big distance. In fact, this was the whole problem with this experiment, and why he received a Nobel Prize for his work, is because, have you ever tried to make something perfectly straight over 35 kilometers? Well, I know the answer is you haven't. So this is really hard to do, okay? Because you got to think, he's putting this in a pipe first of all, so that he can keep all the contaminants and the air and all the dust out of there, so everything's just like perfectly clean. It's just hard to do. It's hard to get something lined up for that long, but he did it. He came up with the speed of light. He's the guy that gets the credit for today. Visits.